be end of the April or first week of May to give sufficient time, even the last class after that. In fact, in IIT, today is the last, Friday will be the last class. Monday exam starts. Please note that these were happening for the last 40, 50 years. Right? Friday will be last working day, last class. Monday exam starts. Not even sometimes Wednesday exam will be, the last class will be there. Friday exam starts. And every day exam will happen. But you have only 2 subjects. Think about 6 subjects. Your IIT MTech students are writing 6 subjects per semester. 2 semesters, they complete all the theory courses. Then they do the project. Okay, fine. Are you able to see the screen?
Yes, sir. We are seeing, sir. Please.
Okay.
Please.
Okay. We will. Okay. Previous class we were started about AC motor. I think you are able to see the motor. This one slides. If I'm correct.
Yes, sir, visible. Yes, slides are visible.
Okay. Hey, Roshan. You talk now.
Welcome, sir.
Sir, nowadays he stopped, sir. Nowadays he stopped. He was so serious and preparing questions for you, sir.
He is not preparing, that means. Okay, fine, no issue. That is not a big issue. Okay, we talked about the AC motor. AC motor, there are 2 types. As I told you in the previous class, synchronous motor. Other one is called induction motor. In induction motor, there are 2 types: squirrel cage and wound rotor motor, or slip ring type motor. These are 2 types. Then I started with synchronous motor. The internal structure, cross section view. It has one is called a stator. Other one is called a rotor, rotating bar, similar to armature and field coil. Field coil, here it is called as stator coil. The armature coil, which is a wound over a rotating part, which is called armature. Here it is called rotor. Okay. But please note that here in the synchronous motor, the stator coil will be supplied with AC voltage. The rotor will be supplied with DC voltage. Okay. That means there's a difference. But later we are going to see that in induction motor, only AC voltage will be given to the stator, and rotor, no DC voltage, nothing. Yeah, induced voltage, because the magnetic flux created by stator induces a induced voltage in the rotor coil, but there's a coil. In the rotor, there's a rotor core on which there is a coil, but you are not supplying any voltage, DC voltage, AC, nothing. And the coil ends will be short circuited. And now, when you supply a rotating magnetic field to stator, that magnetic flux will be cut by the rotor coils. According to Faraday's law, voltage is induced. That voltage in the rotor coil, since rotor coil end is short circuited in case of induction motor, there's no voltage, short circuited. Automatic voltage induced in the coil will supply a current flowing to rotor. They call rotor current, IR. So that is why it's called induction motor. The voltage is induced in the rotor coil because of the stator magnetic field. For stator, we are supplying 3-phase or single-phase AC voltage. AC voltage induces voltage on a rotor coil. Since end of the rotor coil is short circuited, that means the voltage induced automatically current flow will happen. That depends upon IR will be equal to induced voltage divided by rotor resistance or rotor impedance. Because of that, there's a current flowing, that is what called IR. This IR will generate a magnetic flux. That magnetic flux will interact with stator magnetic flux. So repulsion force happen, and the magnetic field try to, or attractive force happens, and the rotor magnet will get locked with the stator, and it will start rotating with rotating magnetic field. That's what we are going to see. That you don't worry. Let us see step one by one. Then that you will understand. Already I had talked about it for understand, because it was little cluttered. Many things I explained: AC voltage, positive cycle, negative cycle, what VRMS, all those things. This slide is cluttered, but I explained step by step. You would have taken notes, but still I am trying to got one more picture. So in which we are going to supply AC voltage. Correct? We are talking about AC voltage. Generally, they call it as RGB. because if you see three-phase motor or three-phase wire in your factory or in your home, there will be 4 wires. One wire will be red color wire, other one will be green color wire, other one will be yellow or blue. Correct? It can be yellow or blue, 3 different color wire, which talks about three-phase voltage applied to the three-phase this one. With a single phase, then your 4th wire called neutral wire. There's a wire called neutral wire with respect to this one. So we are applying three-phase voltage RGB. Here I'm showing blue color. In some books they put yellow color, RGY or RGB. That mentions three-phase voltage. This is a three-phase motor. You can see that the voltage is applied to red color coil. Correct? You can see that the current, for example, from here current, because the supply current goes inside the coil and comes out, and then it comes to, you can see the wire comes and it goes through this and finally comes out and circuit is closed. Correct? So the current flow, this is called IR, red phase. Correct? R represents red phase. Subscript I is the current. Current, this I call VR, VG, VB, blue. Correct? Three-phase AC voltage. We are applying three-phase AC voltage. Because of that, each phase generates alternate, because the voltage supplied is alternating voltage. So the current going through that also will be alternating current. Exactly same that. Because of that, there's a rotating magnet which also same as this. I say that this is phi R, this is IR, this is VR. Same thing for this one. If I say the second one green color means I have applied voltage. Green color, this one, this is a second phase. This is VG, and accordingly there's a current, AC current, same as the sinusoidal. This is IG, and there's a magnetic flux happening here. That also going to be phi G. So phi G is created here in both the phases, and here phi R. Please note that when current flows, there will be a magnetic field is created. That magnetic field will have north and south poles. North and south poles. One is north pole of the phi R, other one is the south pole. Similarly, when you see here and here, you say that north pole of this one and south pole of this. The last one, as I told you, the third result, I am drawing the here. I am applying AC voltage. This is VB, blue color, that is third phase. The representable blue color wire. Please note that voltage will be same as this one. We say phase voltage, phase to phase voltage. There are two things. AC, we will see that when we talk about it. Then you have AC, IB is current, and similarly you have phi B. So three voltages applied to 3 coil. Correct? So this will be north and this will be south. Current enters, flows through this, again goes through this, and finally comes out. The phase is completed. So green color, each one is there. That's what I shown. Okay. So this is, we are giving 3-phase AC voltage for 3 coils. Because of that, current, three-phase current is flowing. And when current is flowing, please know, next slide is going to show that the voltage is not going to remain constant. It is varying sinusoidally, because x-axis is the time, y-axis is the amplitude of the voltage in each phase. Correct? This is time, this is time, this time. You can see that whether AC voltage or the phase, red phase, the voltage is, this is 0 volts. Please note that current 0, all these things are going to 0, 0, 0, and this also 0. And the voltage, red phase 0, it start increasing. How it increases? Sinusoidally. Last class also, it goes to V max. Correct? Each phase has, this is positive V max. Again, it comes down. So again, it reaches 0 volts at a time equal to F by 2. Okay. So this is called one cycle. Okay. One cycle, we say the cycle frequency, if I say 50 hertz, time T, this is called capital T, cycle time, T cycle equal to 1 divided by 50 seconds. So it is going to be 20 milliseconds. If you compute, you're going to be, this time will be 20 milliseconds. Because of that, within 1 second, this 50 times it goes under within 1 second. This is my 1 second duration. The last cycle is this. This is 50th cycle. Within 1 cycle, that's why we say 50 hertz cycle. Okay. So the same thing as all three, but please note that in three phase, the voltage is that is red, green, blue voltage, three phase voltage are increasing exactly same. If this voltage is say 200 volts, this is minus 200 volts. This is also plus 200 volts. This is minus 200 volts. All three phases will have same voltage. Plus 200 volts, minus 200 volts. So, but only thing is, where they reach the peak is shifted by 120 degree. I am going to talk in next slide. Okay. Now that you understand that the three-phase motor, three sets of coil, and the projections are called as poles. They already previously I told that the projection on which the stator is body, laminated magnetic material, on which there's a projection that is called a pole. Correct? There are 6 poles in this motor, or 2, 3 pole pairs, or 6 poles are there. Right, in the three-phase motor. Okay, then you have the rotor. Rotor, it can be a permanent magnet. Correct, this can be a permanent magnet. PM means permanent magnet, or it can be electromagnet. That means only thing is the voltage applied to this coil is a DC voltage, not AC voltage. Plus minus, I say that VDC, this is IDC. Because of that, north and south poles are created. You can see the north and south poles are created. Correct? The current where it is entering, the coil, you can see the coil is wound over like this. Current where it enters, that will become a north pole. Where the current will become south pole. Okay. So because of north and south pole, and how the voltage is given using a slip ring. Correct? Slip ring is attached to the rotor coil, so that the voltage, because otherwise this wire will just get tangled. Correct? As it rotates, you cannot supply voltage directly through wires to the rotor. The DC voltage from DC power supply will be given through a slip ring. That is very important. So the north and south poles is always maintained. Okay, that's how this is the construction, and we talked about it. So now I told you, you are going to supply three-phase AC voltage R, and this is going to be blue. This is going to be G. Okay, you can see that x-axis is time. But also it can be represented in degrees. You know that one cycle of AC voltage takes 360 degree. One cycle of this one. For example, if I say a cycle, for example, green, this is starting where the voltage is 0. Correct? This is a time axis, also can be represented as a angle. Okay, you can represent as a time in seconds, minutes, whatever it may be, also represent this. One cycle takes 360 degree. Correct? You can see that this is positive. It starts with 0, it increases, goes to positive, again comes back to 0, then goes to negative, Vmax, again becomes. This is called as one cycle for the green phase. Green phase, this is one cycle which represents 360 degree. Half cycle go to 180 degree. Now you can see that here all three phases, this is called as a peak value. Correct? This is red peak, green peak, blue peak. If you measure the angle between the peak with respect to this, it will be 120 degree apart. Okay? All three phases will be completed within 360 degree. Will be correct? So you can see that the phase, this is called a phase difference. Between, correct? Between any two phases is 120. Between the first and last phase is 240. So the AC voltage is changing because the AC voltage is sinusoidal nature. This is what we are applying from the power supply, AC supply. So the increases, decreases. So since the voltage applied is varying, the current also will, as I told you that if you see that red color current, I can say that current may be a little lesser. correct? That depends upon just a minute. Sorry. Current will be exactly same as sinusoidal nature, but amplitude depends upon the impedance. IR equal to VR divided by RR, coil resistance, correct? Coil resistance. So this is my IR. Similarly, magnetic flux also will be generated. Correct? I can call it as phi R. Correct? This is my phi R. So that means you can see that magnetic value is 0 and it increases to maximum. This is phi max. Phi max R phase. Okay, and it goes to a maximum value. Again, it comes to become 0 because current is become 0. Again, negative phi max because I have this one. So that means it also is varying. If you see with this one, this is what we call a rotate. Same thing happens for all three phases. It creates what we call a rotating magnetic field. Okay, rotating magnetic field is created for each phase. Since at any given time, only see one phase is always greater than other phases. That you can note down. You can see here the voltage. If you take this R phase, the voltage is maximum V max. Correct? At that time, what is the, if I draw a vertical line, what is the voltage of the green phase? Only this much. The voltage is from 0 to this much positive side. Correct? Maximum I say 200 volts. Red phase. During that time, blue phase and green phase are negative voltage. Negative maybe 50 volts, something like that. Correct? So both are, because you can see the both as well. So which has maximum? The maximum current will be flowing through R phase. The magnetic flux created R phase will be more compared to other two phases. But you can see that as this phase is start declining, the green phase is increasing, correct? After this, the green increases more. So that means at any given time, the magnetic flux created red, green, blue will be peaking compared to other two. So the resultant magnetic field will be a rotating magnetic field. I am going to show in the next slide how it works. Okay. So how the rotating magnetic, because I applied three-phase voltage, which is each voltage 120 apart, and this is given to the three-phase coil of the stator, and the stator creates a rotating magnetic field. Correct? That's what I mentioned as pi m, magnetic field. Okay. So you can see bottom, I get driven here this one. So this is nothing but my rotor. Correct? Rotor has north and south pole. Arrowhead is north. Other base, this is called a south. This is north. This is south. This is north. This is south. Correct? You have one rotor only. It is a permanent. It is a DC magnet, or it can be a permanent magnet. I am supplying. So this is north. This is south. North, south, north, south. How it works, I am showing here. See, as I told you, at a given time, for example, this phase 1, correct? Phase 1 is nothing but here I shown is blue color, because little dull, looks like black, but it is a blue phase. Blue phase is peaking. And previous diagram, time diagram, I said R is shown as first, but it can be anything for under, because you can start with any phase, phase 1, phase 2, phase 3. Blue phase I am taken as 1. Now, that means this is at maximum voltage. During the time, other voltages, this is lesser. Red is less. Green is under negative voltage, correct? So now, since the blue phase is energy, that is phase 1. I call this as phase 1. Correct? Blue phase 1. Phase 1 is magnetized. Okay. Now, this is south pole. This is the north pole. Because a current flowing in this coil, we will say that this pole, correct? We call a pole pairs. In three-phase motor, 1 and 2. This is for blue, this one. This is 1, and I can say the R. Sorry. Okay. This is R. This is R dash. Okay. This is blue. This is blue dash, correct? Blue dash is one pair, blue is another pair. When blue is in north, this one pole, that time this will be B dash will be south pole. Okay. So similarly, when this is north pole, this will be south pole. R dash, correct, will be south pole. Similarly, green this one. Now, from this, you can understand that at this instant, at this time instant, blue phase has the maximum magnetic field and it attracts the rotor magnet, correct? Rotor is a permanent magnet. Already told you, rotor is a permanent magnet. Okay. Now, my blue phase becomes south. This is south. This is north. What will happen? This magnet will be attracted by this. Correct? This is attracted by this. Automatically, this will be attracted because south pole of the rotor is attracted by north pole of the stator of the blue phase. Correct? Here it is phase 2. It is same. You can understand. Similarly, this is attracted south pole of the stator, blue phase stator, attracts the north pole of the rotor, which is a permanent magnet. That means this will rotate. Torque is produced. Big attraction force, we call it a torque. That means it will align like. Correct? You can let me clear this. You will see that. This after some time, the rotor will be attracted. This is north pole. This is south pole. This is south pole. This is north pole. Because at the time instant, correct? In the particular time instant, this has become south pole because peak maximum, this one, flux is there. Correct? 5 Bu. This is maximum. So it aligns. Afterwards, you can see that next, the blue phase, in case this is red, correct? Actually, this is what there is shown a blue. Instead of red, you can imagine, correct? And so after the, so there's no need to go back here. We can use this itself. So this is the blue phase. I call it as phase 1. This is the red and this is the green. Correct? I call it phase 1. No confusion. Please remember. So this is the north pole. This is the south pole of the rotor. Correct? Arrowhead. Correct? So when blue phase is in peaking, the rotor may be something like this. It may previously before this one, it may be like this. It was attracted by this because this is south pole and this is north pole. So this rotated like this so many degrees and aligns. Correct? The rotor aligns. Once aligns, you can tell that this is a north, south, this is south, north. So it stays at this instant. After some time, you can see the red phase become, correct, maximum this one. But this is not a step, but is continuously varying. For understanding purpose, actually, as this is decreasing, this is increasing. Correct? From peak, it is decreasing. This is increasing. At this point, at this time, you can see both are equal. Correct? Both are equal, but this is a negative. And after that, this is start increasing. Okay? If you draw the resultant vector to every time instant or every phase angle, correct? So always one phase will be the maximum voltage, maximum current, this one, compared to other two. Accordingly, that phase will be attracting the rotor, which is free to rotate. It is a permanent magnet. So at this instance, you can see here, this is what the second phase. Second phase, the red phase become maximum voltage. Okay. You can see that at this instant, the blue will become this much only. And the green is still negative, correct? Green is negative. Blue is positive, but less voltage. But red has become maximum. Previously, here blue was there. So automatically, what will happen? This is south pole. This is north pole. This is north pole, south pole. So this has been attracted by from here. It has rotated. You can see that this is rotated from here to this angle. So many degrees rotated. 120 degrees rotated. It aligns and stops. But please note that it doesn't. This actually it is moving continuously from here. This was moving like the continuously moving. If you draw the resultant magnetic field of all three, you will see that it is happening. But for understanding purpose, I shown 5 time instances. Which time instant? 1 time instant, 2, 3, 4, 5. Correct? Or I can extend to 6 also. Correct? So first time instant, the blue phase was maximum this one. So it attracted this magnet aligned, rotor aligned. At this time instant, the red phase is the maximum field strength. So it has attracted this, rotor is rotated this one. Next, green phase. From here, this is rotated this one. So you can see that now it has originally somewhere it rotated this much, rotated this much, rotated. After three peaking, the rotor, which was like this, is come to a new position, correct? So it was something like this. Understanding purpose, we can say that it was like this. Now it has rotated this much degree, and this much degree. All three phases. Again, you can see that again blue phase is peaking, correct? From blue, again the rotor from here is moved to this many degree. Next, again red phase. So you can see that continuously, because the AC voltage, which is sinusoidal in nature, all three are equal strength, but they are separated by 120 degree. And the magnetic field, the resultant magnetic field, which attracts the rotor, correct, is passing from one pole to one pole, next pole, like this, correct? So by the time you will see that within the 2 cycles, the rotor would have rotated 360 degree. Correct? So this is how the rotating mean. So what we say is how it works. You have a AC magnetic field. In fact, I call AC rotating magnetic field. No, correct? Generated by AC rotating magnetic field, generated by stator coil. Stator coils, there are 3 coils because of AC voltage applied to stator coil. AC will apply. So AC current flows. So AC magnetic field is, which is also increasing, decreasing. Because of that, the rotor. So what it does is, initially the rotor was like this. I told you, maybe somewhere before you apply the voltage, the rotor can be any position. For example, it was like this. Correct? No, you have not applied any voltage to stator and rotor. Okay. Rotor applied voltage. This is north pole, south pole. And you are not applied AC voltage. Once applied the AC voltage T equals 0 time, the peak, the voltage start increasing. This also increasing. This also, everything is varying. But at the time instant, the blue has the maximum, understanding purpose. So this are pulled, and it align with this at this time instant. And after this one, since you can see that the red phase is increasing, crosses blue. The maximum voltage is resultant magnetic voltage, red phase maximum. It reaches maximum at this time instant. So this is pulled and the rotor aligns like this. Rotor align is second instant. And third is, that means for phase 2, when it is maximum voltage is there, rotor is like this. When phase 1 is like this, rotor is like this. Correct? Rotor is like this for this phase, this one. And but please note that it is continuous, not the step. It is varying. This voltage is decreasing. This is increasing. As a resultant voltage at this time instant, if you consider the phase 2 become maximum, rotor has rotated so many degrees and aligned like this. Then green phase again rotated from here, it aligns. So when I give 2 rotations, automatically my rotor has rotated 360 degree. So how it is? This is the rotating magnetic field attracts the rotor, okay, north and south poles, which is a permanent magnet. You know that north pole attracts south pole, correct? So, south pole attracts north pole. So the magnetic field get locked. We say that initially, synchronous motor, when you give the voltage, AC voltage to 3-phase, and rotor with the DC voltage, it may be somewhere, correct? The rotor can be somewhere like this also, middle position also, okay? But first thing is, it has to get locked with this, correct? So when this voltage give a maximum voltage, correct? Blue phase become phase 1, become maximum. That time, you have to make the rotor to rotate and get locked, correct? That is called a magnetic locking. In synchronous motor, if you give just to give 3-phase voltage to stator and a DC voltage to the rotor, the motor will not run. It will not start. In synchronous motor, one of the issue is starting, correct? Starting synchronous motor, I can say the sync motor requires external motor, one more motor. The another small motor will be attached to the rotor of the synchronous motor, and at that time the load will be disconnected. For example, you have a 3-phase synchronous motor and it is connected to load, right? And if you give the 3-phase voltage and a single phase DC voltage here, correct? Single phase DC voltage here to rotor, and this is for stator, the motor will not rotate because first time is it has to get magnetically locked. You have to lock it. Physically, you have to rotate this rotor so that its magnetic field comes closer to the stator magnetic field and get locked. Okay, so that means you will attach a small motor which is called a starting motor. In synchronous motor, you need a small starting motor which will rotate the rotor so that the rotor magnetic field, north and south pole, will be get locked with one of the phases, whichever is P condition. So that way, once it get locked, then your starter motor can be disconnected. Maybe you have a clutch, you disconnect it. After that, the rotor is locked. So with rotating magnetic field, the rotor also start rotating. Starting alone you have to do. This is one of the drawback of synchronous motor. But synchronous motors are still used. They have advantages. Okay, so you understand this? Any doubt? Because this is understanding very important. Otherwise, you won't understand including induction motor. Correct? So now, what is the speed at which the motor will run? That depends upon what you call the synchronous speed of the motor, which is called as NS. Note down. Synchronous speed of the rotating magnetic, synchronous speed of rotating magnetic field. Note down. We are giving 3-phase because of that synchronous. So 3, what is that is represent, N represents speed, sub 3 represents synchronous speed. NS equal to 60 into F by P. Okay, radians per second, or 120, correct? We can say that 120 F by P. Okay, so you know the rotation speed can be mentioned in terms of radians per second, correct? Or cycles per second. Okay, 60 F divided by P, where F equal to frequency of the power supply. Frequency of AC power supply. To AC is given to stator winding. For clarity I'm writing, AC voltage given to stator winding. In India, it is 50 Hz. You know that power TNEB, Tamil Nadu throughout India, electrical grid. That frequency, if you give the voltage to the synchronous motor, F should be taken as 50 Hz. Okay, then P is the number of poles. P equal to number of poles. Okay, 60 is a constant, correct? You can write 60 F by P or 120 F by P. Okay, so you can use any one of this formula. Okay. Okay. Yeah. Before, what is that means? You can see that this formula I write capital P. Here I written small p. Correct? The capital P represents pole pair. Correct? How many pole pairs are here? This is one pole, red pole, this is another. Together it is one pole pair. Capital P, 1P. And again, I have second, another one capital P. Then this is the third capital P. That means pole pair means I have 6 poles, because we know that opposite pole pieces are wound using same coil and same voltage is applied. In the previous slide I showed, correct? You can see that R phase is given, the voltage goes through this coil and come back and close this and ends up. So together this is small p, this is small p. Okay, together they become capital. Pole pair means 2, pair means 2. So if I want to compute the synchronous speed of the motor, I can use 2 formulae. 60 F by capital P is nothing but this, we have to 60 into 50 in India, correct? My speed, NS, rotating magnetic speed of the synchronous speed of the magnetic field, not the motor speed. Okay, divided by 3, correct? Pole pair, 3 pair, correct? Going to be 0. Correct. So this is going to be so 1000 RPM. The motor speed will be 1000 RPM. NS. Sorry, not motor. Rotating magnetic field speed. Correct. Rotating magnetic speed NS, synchronous speed, which is called a synchronous speed of the magnetic field, be 1000 RPM. Instead of that, I can say that NS equal to 120 multiplied by 50 divided by 6. Correct? So, because I am talking in terms of number of poles. Number of poles are 6. 1, 2, 3, 4, 5, 6. Or again, this is also going to yield only 1000 RPM. Correct? So, synchronous speed of the rotating magnetic field can be computed with this formula. Okay. Okay. Now that I said, we talked about how the synchronous magnetic field is created, which is very, very important for the AC motor working. Whether induction motor, all this thing work in the same principle. So the rotating magnet is created by supplying the AC voltage to three-phase coil, which are separated by 120 degree apart physically inside the motor. Correct? They are shifted by 120. You can see the poles. Correct? These poles are shifted by 120 degree. Pole pair if you see. Okay. So voltage current also apply. So the rotating field is created. The rotating magnetic field get locked with the rotor gets locked with the rotating magnetic field, which is invisible. Please note that magnetic field invisible. So automatically the magnetic field, rotating magnetic field from the each phase pulls the rotor like this, and so the rotor rotates. So torque is created. The force is created by the interaction between attractive force between pole magnet and the rotor magnets. Okay. So to calculate the torque generated in the motor, we need to understand how the synchronous motor works. So here, this figure, please take the figure, very important. Here I am shown a diagram. The red one marked with this is nothing but stator magnetic field. Correct? Stator magnetic field, which is the body in the, it is at a put, the coil is put on the stator, which is nothing but body internally. Correct? You have grooves. I will show in the next class something physical motor. There will be a lot of slots in the something like this, in which the coil will be put. Grooves will be there. Correct? Laminated grooves in which three phase will be throughout the body. Correct? And which alternate will be, this will be red phase, this will be blue phase, green phase. Again, red, green, blue. The wires will be, coil will be inserted so that when voltage is given, the rotating magnetic field, you can see that I have drawn the direction of rotation. That means the magnetic field is rotating like this. Okay. Oh, fine. So and I given the rotating speed of the magnetic field NS, capital NS. Some books they put small NS also, it is same. Okay. Now there are two magnetic field. One is called stator magnetic field. The magnetic field at the given instant, take one instant. At this instant, you can see that magnetic field is represented by green color. Correct? So the line I am drawing, this is called magnetic axis of the stator field at given particular instant, but it is not going to be constant. For understanding purpose, you need to, in the exam, you are expected to draw this diagram. Okay. Then at the time instant, the rotor, correct? My rotor magnetic field is this. Again, I'm drawing, you can see that this is the center of the rotor. This is black color circle is rotor, and this is my direction of magnetic field at that instant. Correct? We generally represent magnetic is a vector. Correct? So this is my stator field. This is my rotor field. Correct? Rotor magnetic field represented by F subscript R. Correct? Rotor. This is F S. Okay. Now we can see that between these two fields there is a angle. Correct? Because 360 degree. This is called as lambda. This is called a lambda. Right? Lambda is the angle between the rotor and stator magnetic field. at particular instant. Okay. Now, because the two magnetic field, because of both are interacting, there will be resultant magnetic field, which is shown in another gray color. You can see that. Yeah, this is the resultant magnetic field between the stator magnetic field and the rotor magnetic field. This angle is called as lambda, correct? The lambda is the angle between rotor and stator magnetic fields. Okay. Now, this angle between the resultant magnetic field, correct, and the rotor magnetic field, this is called as delta R. Correct? This angle. Similarly, the angle between the stator magnetic field and the resultant is called as delta S. Correct? They are called as delta R and delta S. The total angle is called phi. The total angle is called as phi. Okay. Now, due to now that, as I told in the previously, once we apply this one, the stator is correct. Stator magnetic field is phi lambda angles away. Correct? Lambda angle. This is lambda angle. This is away. But it should move and get locked with this north and south pole. Please see that north pole of the stator is on left side, south pole of the stator on right side. The magnetic axis is like this. Again, here the north pole of the stator is here, south pole of magnetic, the magnetic axis is this. The resultant magnetic field is this. Because of this, correct, the magnetic field of the stator attracts the rotor, correct, which is aligned like this, and correct, attracts towards this, correct. So similarly, this side also it is attract. Then this south pole of the rotor is attracted north pole of the stator, and north pole of the rotor is attracted by south. So finally the rotor should align something like this, correct. South here, north here. That means this has to move, correct. So you can take this figure. This figure you have to draw in the exam. Expected to draw this and explain how it works. So we know that resultant field, magnetic field Fr, and rotor field called Fr, small capital Fr. Capital Fr is resultant. Small R represent rotor, and small Fs is the stator. Now that you know that. Now, when I give initially, when the power is given, as I told you, due to the inertia of the rotor cannot go and catch atom on its own. Correct? Rotor has a mass. Correct? Please note that rotor has a mass. Correct? It has a mass, and the mass will not allow the magnetic flux field of the stator is not sufficient to attract this one and pull it. So that means you have to rotate this one, align like this. We need to align the rotor using external this one by attaching one more starter motor. Okay, and rotate it physically, so you just get locked. Then once it is locked, then you can disconnect this. That's what is mentioned here. Okay, non-self starting, because of this only synchronous motor cannot start this on its own. By using an auxiliary motor, rotor is run to close to the synchronous speed of both the field. That means we know the synchronous speed. How will you find out? Synchronous speed ns equal to 120 F divided by P, or ns equal to 120 F divided by small p or capital P. And you know that depends upon number of rotors, all those things in the given problem. Then you have to rotate your rotor initially, so that it just get locked with the rotating magnetic field, north and south pole, align like this. Okay, so north and south, they can rotate together. Okay, so this is south, this is north. Okay, any doubt in this? I just want to complete this, and so that we can. I know that it is, yeah.
No issue, sir. Okay, sir.
Okay, so figure you want to see? Shall I go to next slide?
Yes,
I
sir.
think
Yes, sir.
you would have noted this figure also. In the exam, you are
Yeah,
expected
we
if the
noted,
question
sir.
is
This
asked.
is not-
These two figures are important figure. Now we know that in synchronous motor, I say sync motor. Formulas are important, note down. Synchronous speed of rotating magnetic field. Represented by Ns equal to, already you know that, 60 F divided by capital P or 120, extremely sorry. 120 F divided by small p, where P is called per pole pair. Small p is called as poles, number of poles. In the exam, if you are given, say, 8 poles, I am not going to give 8, correct? So 12 poles, correct? 6 poles, correct? Then you have to use this. And if you want to use that, the number of poles, I say 12 poles divided by 2 is giving pole pair, that should be substituted here. If I give 6 poles, it should be divided by 2, this will become 3, and this will become 6. So if you use wrong formula, you will get wrong speed after the, because you are going to do other calculation based on NS. Everything will become wrong, then you will get 0 mark. Careful. Okay. So we know you can use any one of that, but you should know what it is. Read the question, then you will understand. Okay. So now F is the supply frequency. In that already we know that F is called as supply frequency. In India, generally we say 50 hertz or 50. Supply for F equal to 50. Okay. Now, main important characteristics of synchronous motor. One is the synchronous motor. Synchronous motor, we are talking AC synchronous motor, will run either at sync speed or close to sync speed. We'll say why it is later. Close sync speed. Sync speed means the magnetic field is rotating. Its speed already we calculated 120 F divided by small p or 60 F by capital P, and you have calculated 6p already say 1000 RPM, correct? That is magnetic field rotation. The rotor speed, which is called motor speed, can be maximum of 1000 RPM. It cannot be more than that. But many times it will be slightly less. Correct? Rotor speed or motor speed, both are same. Rotor is nothing but on which you are going to connect rotor. Its speed will be always lesser than the synchronous speed because of there's a time lag, correct? Catching up at the maximum speed. Maximum speed will be rotor speed and synchronous speed and rotor speed. NS is called as synchronous speed. NR is called as motor speed. Some books they call it NM, correct? These two will be equal when no load condition, very less friction, correct? And small motors, and that also the inertia of the motor is less, correct? The mass of the rotor decides, and also the less friction, good bearings, all those things. NS can be NR, that is called rotor or motor speed. That also very this sort of speed. But many times NS will be greater than NR. Not too much. It can be few RPM. Correct? So we say the synchronous motor will run either at sync speed or close to sync speed. It cannot be run at any other speed. You cannot run the motor at 500 RPM, 600 RPM by varying voltage, current, whatever you do, it cannot be changed. So synchronous motor will run close to NS, no load condition, and loaded condition slightly less, but only. So generally what they say in books, synchronous motor will run only at sync speed, correct? Otherwise it won't run. Only at that is very important. It is a constant speed motor. It is a constant speed motor. 3. This constant speed, the speed depends upon frequency supply and the number of poles. In the equation, see, we know that it will run at constant speed, generally close to NS, which is called synchronous speed, rotating magnetic speed. The formula clearly states, correct, 120 F divided by small p, correct. So where the P is number of poles and F is the supply frequency. Once this is fixed, in India, it is 50 Hz. You go to US, in India, 50. Go to US, it is 60. You go to France, it is 70. Correct? Japan, something else. Most of the Commonwealth countries, British ruled countries, except US. Correct? All other countries are following 50 Hz. Around 20 to 30 countries. Correct? And US follows 60, and few other South American countries, they buy equipment, motor, all the USA, because they did not industrial this one for last 100. Now they are caught up. So they are also adopting 60. Few of the countries. And France uses 70 Hz. The supply frequency France is 70 Hz. Okay. So that means the F will be fixed in the world. Correct. Only the any one 50, 60, or 70. And P number of poles. It can be 6 or 12, something like that. Depends on what is speed you want. You decide what is speed you want for given this one. Accordingly, poles also you can, while designing motor you design. So it runs at the constant speed only. Correct? It is not self-starting. It cannot start itself. You give the stator with 3-phase, rotor with a DC voltage, motor will not run. What you have to do? You have to put additional mechanically coupled. The rotor will be coupled to a small motor we call starter motor, and you have to run the motor such that the motor, which is starting motor speed, is same as synchronous speed. We said 1000, correct? Synchronous with 1000. That means rotor should be rotated. By giving DC voltage, in addition, you have to make the rotor to rotate at 1000 RPM. And when you are doing, at some instant, automatically, the rotor will be magnetically locked to the magnetic field stator. After that, you can disconnect the starter motor, and then you can connect your load. The motor will be able to take and maintain the constant, not self-starting. So you need additional this one. Then the last one is it can work on leading or lagging power factor. Okay, so it can. These are the main important characteristics of the motor, and I stop here. Tomorrow we will continue the other. Excuse me. Tomorrow we'll continue about the torque equation and the phasor diagrams and the speed, torque, curve, power curves, and other important types. There are 2 types of how they are working. What is the difference? One is called salient pole motor. Other one is called a non-salient pole synchronous motor. Those difference we'll see. After that, we'll start in the induction motor. Okay. Tomorrow I'll complete first of this. Next we'll start our induction motor. Thank you.
Thank you, Mr.
Thank you. Kind of you. Have a nice day.
Thank you, sir.
Thank you, sir.
Give your attendance without forgetting. Important. That is important.
Thank you.
Yeah.
Thank you, sir.